Hello. In this video, we're going to start chapter 4 on bijection and cardinality. It's really cool stuff. This video is going to be a long one, I think. We're going to talk about how we write down numbers or how we represent natural numbers on a piece of paper, how we write it. It seems like a intuitive thing that we know instinctively because we practiced it throughout our lives, but it's actually really clever, and there's mathematics that goes behind it, which is useful in future constructions as well. So we'll spend some time going through it. Bit of a warning, this is a very involved proof that we're going to prove in this video. So it might warrant more than one watch. Anyways, let's jump right to it. Okay, so I want to start by saying our number system is very versatile and it's very awesome. So what I mean by number system is how we write down numbers. Like here's an example of how we write down a number, 538. We might compare this to how you might write this in Roman numerals, right? Which sometimes we repeat symbols to mean, or 3, I means 3, and 3 X's means 3 times 10. And you might have to learn symbols as we get to larger and larger numbers, like V stands for 5, and D stands for 500. So with the Roman numeral system, sometimes repetition might be necessary to add on to those symbols. And you might have to learn a new letter for each as the numbers get bigger and bigger. So you might run out of letters if you're talking about enormously large numbers. But even Roman numeral is way better than maybe hash marks. Like jotting down exactly how many times you wrote down the dash or slash as one representing number 1, and then you keep adding them. Writing down 538 in the system would be horrible, as you might be able to imagine. But it goes beyond that. If you wanted to represent numbers as large as atoms of the universe, 10 to the power of 80, you don't even have enough space to write down all the hash marks, because you're using up more than one atom for each dash that you write down. And you might be able to write down something small in scale, such as diameter of a proton, which is 10 to the negative 15th meters, which is 1/1,000,000th of 1 nanometer. So our system is very clever, and I want you to kind of step back and appreciate that, and prove some math about it. If you have taken or are currently taking math history, you might know there are other number systems as well that that might not work as well as ours. Okay, so let's talk about our system. Let Q be any natural number greater than 1. So I'm thinking of Q as our base. What we do is base 10 system, but you could have something similar for any different base. So if we pick a Q, like a 7 or something, then we can create a 7-ary or base 7 representation of any number n, any natural number n, as a list of coefficients. And these coefficients will range anywhere from 0 all the way up to 1 less than the base. With base 10 system, we're looking at 0, 1, 2, all the way through 9, 10 minus 1. If you're looking at binary system, like a q-ary system, you look at just the digits 0 and 1, because 1 is 1 less than 2. Or if you're looking at 7-ary system, you use coefficients 0 through 6. There's some rules about these coefficients though. The leading digit has to be positive. So when we use a q-ary system, we don't use 0 as the leading coefficient. And how we write down our number, n, is going to be sum of powers of the base. So if ai are the coefficients, a1, a2 through am, you multiply that with some power of the base. So in our decimal system, powers of 10, and so on. And we should be able to write down any number n, natural number n, in this way. So let's look at some example. So base 2 only uses digits 1s and 0s. So 1 means 1, 1, 0 means 2, 1, 1 means 3, 1, 0, 0 means 4, and 1, 0, 1 means 5, and so on. If it's base 3, you use digits 0, 1, and 2. So counting from the left, that's 1, 2, 3, 4, and 5. Our base 10 system, decimal system, you're familiar with. We use all the digits up until 9, and then you wrap around and start over again. So if you're a computer scientist, maybe you're familiar with binary. You might also be familiar with hexadecimal as well. Hexadecimal is base 16. So we usually have our 10 digits or 0 through 9. But for hexadecimal, you need a digit that goes all the way up until 15. So you might substitute like letters all the way up until A through F. So A means 10, B means 11, C is 12, and then 13 and 14 and 15 is F. And then after that, you wrap around to 1, 0. And that's 1, 0 is 16 in hexadecimal. I hope this makes sense. And there are other systems that has been used in the past. Babylonians used Base 60 System. And some of that influence we use today as well. For example, the system we use for time, 60 seconds make 1 minute, and 60 minutes makes 1 hour. So that's definitely an influence of Babylonian system, where 60 of them increase it to the 1 on the next place. Also, angles as well. If you talk to most mathematicians, they like radians better, but people are used to 360 degrees in a full circle. So 360 is not a 60, but it is a multiple of 60. And if you divide up 1 degree into smaller pieces, you can divide up 1 degree into 60 seconds, 60 minutes, and 1 minute could be divided into 60 seconds as well. So you can kind of, if you fine tune in the angle sense, you're using Base 60 system as well. The reason why you might use something like 60, why 60? 60, a lot of numbers divide into 60. You can divide it by 2, you can divide it by 3, you can divide it by 4, 5, 6. You can't divide by 7 or 8, but or 9, but you could divide all the way up until 6, which is nice if you're doing division. Okay. All right, so let's practice using these notations. So what we're gonna do is when we write down a number, to distinguish this number from other bases, what we do is, if you wanna indicate that we're writing in a different base, in subscript, we might write down in parentheses, what's the base we're using. So if I write 538 with base 10, this is how you might write that. And the real meaning behind this number is that I'm adding different numbers of different powers of 10. So, for example, the 5 in the 538 means we're using 5 times 10 to the second power, 5 times 100. That represents the first digit. And on the 10th digit, we have a 3, so 3 times 10 to the first power. And then one's place we could write down by any base to power 0 is going to be 1. So 8 times 10 to the 0 is going to give you the ones place 8. And you add them up, and that's what the number it's supposed to represent. We could do this with other bases as well. So if I write down 101010 in base 2 system, we count from the right-hand side. So this is the 0th power, 1st power, 2nd power, 3rd power, 4th, and 5th power. So the leading digit 1 is going to be multiplied with 2 to the 5th. That's 32. And we don't actually have to write down zeros, but the next place is 0 times 2 to the 4. That's 0 times 16. And then the next place is 1 times 2 to the 3. 2 to the 3 is 8. And we could skip this one. 1 times 2 to the first power is just going to be 2. And then no ones place. So if we look at the surviving terms, 32 plus 8 plus 2, there'll be 42 in base 10 system. I hope that made sense. So if you think you got what I mean by this, I want you to pause this video and try to write down what 213 is in base 5. So pause now and try it out. Okay. So what this is saying is 2 times 5 to the power 2 plus 1 times 5 to the power 1 plus 3 times 5 to the power 0. 5 squared is 25, so 25 times 2 is 50. 1 times 5 is just 5. And 3 times 1 is just 3. So in base 10, that's 58. I hope that made sense. So, okay, that's how you go from different q-ary systems to base 10. But how do we go backwards? So if I had 58, and if I wanted to represent it in 5-area system, how do you do that? So what you do is basically division. So here's what we do. So you first ask the question, what's the largest power of 5 that's less than 58? So you might try a couple times. So 5 squared is 25. 5 cubed is 125, which is too big. So 5 squared is the largest power you can get. So that's where we're going to start. Then you ask, how many 25s can I remove from 58? And we can remove 2 times 25. So we remove it. So we record down how many of those copies we removed, and then we subtract from the 58. So if I take 58 and subtract 25 twice, I'm left with 8. And then you ask the question, well, what's the goal? You go down 1 in power. So now we're looking at 5s. How many 5s can we take out from 8? We only can take out 1 5. So we take it out and we're left with 3. And then we ask how many 5 to the 0th power, how many 1s can we take away from 3? And that's 3 of them. So 3 minus 3 is going to be 0. And if you're working with natural numbers, you can always subtract 1s until you can get to 0. So this is where the process ends. Okay. And if you record down how many copies of each power you were able to subtract, 213 is going to be how we write down that number that we started with, which is 58. Okay. So I want you to try it again. So let's say I take the number 538, and this is in base 10. I want you to change this to base 7. So see if you can do that using this method. So pause the video now and try it out. Okay. So let's try to write this in base 7. So let's look at different powers of 7. So let's see. 7 squared is 49. I think I can make it bigger. So 7 to the 3rd power is 343. So that's the largest power of 7 I can subtract from 538. And I can only subtract 1 copy of that. So 538 minus 1 copy of 7 cubed we get 195. Okay. Now I look at a smaller power of 7. So 7 squared is 49. So I can't take out, not quite 4 copies of 7. I can only take out 3 copies of 7 squared. So 195 minus 3 times 7 squared is 48. Okay. So now I'm trying to subtract copies of 7. So 7 times 7 is 49. It's less than that. So I can take out 6 copies of 7 from here. So 48 minus 6 times 7 to the 1st power. So 48 minus 42 is 6. And you can take out 6 copies of 1, you get 0. So we write down how many copies of each power we subtracted. So 1, 3, 6, 6. So this means 538 in base 10, written in base 7 is going to be 1, 3, 6, 6. Okay. All right, I hope that made sense. Okay, so let's get to the big theorem in this video. So let's pick a base q. And base q, any natural number greater than 1 Once we pick a base, every natural number has a unique base Q representation with no leading zeros. So this is what you might call existence and uniqueness type of theorem. So we have this new construction of q-ary system. For this to be useful, it'd be nice if every number could be written in this way. So that's not obvious just from saying, well, base means you use different powers of those numbers. Okay, but it's unclear if every number could be written as such combination. So that's one thing, the existence of base Q representation. And not only that, it would be very useful if there's only one way to write it in that base. So if you've written two different combinations of different powers of 7, for example, then if it's a different combination, it's a different number. That would be a useful fact to know. So there's two parts to it, existence and uniqueness. They will both take a little bit of work to prove. So let's start with existence. Okay, for existence, we're gonna use induction. So the base case is easy. So we're using number 1. I want to be able to write down 1 in different representation. Well, anything to the 0th power is 1. So we just use the coefficient, the power of 0, the 1's place. The coefficient is going to be 1. And 1 times any base to the 0th power is equal to 1. So we were able to write down in base Q the number 1. It looks the same in every base. All right, so base we feel like we got for free. Let's do the inductive step. So, okay, so let's say there exists a q-ary expansion, or when I say expansion, I mean representation as well. If there exists a q-ary expansion for natural number n, I want to be able to write down the next number, n plus 1, in a very similar way. Right? Now, remember the rules. These coefficients could be anywhere between 0 to q minus 1. And the leading digit cannot be 0. Okay. So we're going to do it in different cases. So suppose all of the coefficients is q minus 1. Okay, so if this was decimal representation, this is the case where the number is 999,999, something like that, where we're maxing out all of the digits with the highest digit available. In that case, 9. Then when we represent that plus 1, what we're going to do is we're going to add a new coefficient. On the next coefficient, we're going to use the digit coefficient 1, and every other digit below it is going to be 0. So we're carrying 1 over to the next step. Okay, now I have to convince you that that gives you a number that's 1 larger than what we had before. So let's write it down. So this is n, so this is 999,999, is represented with 10 minus 1 with every power of q up to that point. Q minus 1 is constant here, where it doesn't depend on j. So I'm going to pull that outside of the summation. I'm going to factor it out, and I'm going to get this next expression. Okay. And then here, I'm going to use your homework. I think this was homework problem 3.35. You prove this with induction. So if you add up all the powers of q from 0 to m, I think in the homework it was 0 to n minus 1, and then you end up with the power n. But if I replace n minus 1 with m, the power we're going to end up here is n plus 1. So this is the same thing as this quotient. That was the content of the homework. And you might notice that now the q minus 1 in front and q minus 1 in the denominator will cancel out. And we just get q to the n plus 1 minus 1. That was the nth step. So if n is equal to that, then I can bring the negative 1 over to the left-hand side by adding 1. And then I end up with n plus 1 is q to the n plus 1. And that's exactly what we have for the new representation. We have 1 of the next power of q and plus 0 times all the lower power. So that is equal to n plus 1. So we've got it. Okay, so that was the special case where we had to like carry the 1 all the way to a new digit. Okay, so if that wasn't the case, then there's just some coefficient in the expansion that is less than q minus 1. So that was a special case where everything was 99999. If it wasn't that, then there was some digit that's smaller than that. So let's say t is the index, the smallest index, so the closest to the ones digit, where it's less than the maximum coefficient you can have. So we're gonna denote that index by t, and we're gonna define a new set of coefficients. So the coefficients is going to be the same for every coefficient above the special index t. On the coefficient of the index t, we add 1 to it, and we can do that because it's not the maximal digit q minus 1. And everything smaller than that, we're gonna replace with zeros. And what we wanna show now is that we have a new set of coefficients. So these are the coefficients bj's. That is the same thing as compared to the previous aj's plus 1, because we want to be able to represent the next number in the q-ary system. So that's our claim. And basically how we prove it is similar to what we did slightly earlier. So what we're going to do is first cancel off all the leading coefficients. So all the aj's where j is the index that's beyond t, all of those are the same here and here. So we could subtract those off. Okay. So now the leading, so if you subtract this off from both sides of the equation, because they're the same, on the left-hand side, what we have is the at plus 1, that's the one we have where the index is exactly t. And on the left-hand side, everything else is zeros. So I don't have to write anything else on the left-hand side. On the right-hand side, we have the 1 here. And on the tth index, we have a sub t, which is 1 less than here. And all the index below it is q minus 1. So we have q minus 1 multiplied by different powers of q all the way up to the power t minus 1. Okay, so we have a sub t times q to the t here, and a sub t times q to the t. So you could subtract that off from both sides. And what we're going to be left with is q to the t on the left-hand side. 1 we're going to carry over, and we have this sum of all the lower digits, which is all q minus 1. We're going to do the same thing we did earlier. We're going to factor out q minus 1 from the summation. We're going to use the homework problem to rewrite that summation as this quotient. Again, q minus 1 is going to cancel out. We're left with q to the t minus 1. The 1 here and minus 1 there cancels out. And we just checked that they are indeed equal to each other. Okay. So what did we show? We showed that this q-ary expansion plus 1 is represented by this. So n plus 1 q-ary expansion for n plus 1 is that. Okay. So therefore, n plus 1 has a q-ary expansion. Phew. So that's the existence part of the proof. Now we want to show that there's only one way to do this. So we want to prove the uniqueness part of this representation. There's only one way to do it. So we're going to do that by what's called method of descent. So remember, method of descent is kind of like what we do with contradiction. So what we're going to assume is that, okay, maybe it's not unique. Maybe number n could be written in 2 different ways. So if there is like an exception, there's a number that can be written more than one way, then we're gonna pick a smallest number n that could be written in 2 different ways and see if we can come up with something that's impossible. We're gonna come up with a contradiction. Okay, so let's say n is the smallest natural number with the q-ary expansion that is not unique. So you pick 2 different q-ary expansions coefficients, AR through A0 and BS through B0. So now the leading digit place might be different because it's a 2 different q-ary expansion. So let's eliminate that case first. So if there's different number of digits, let's say R is not equal to S, then one of them is going to be bigger than the other. So assume without loss of generality that R is the one that's bigger. So if S happened to be bigger, you just relabel it, and the argument is going to be the same. Okay, so let's say R is the bigger one. So this has more digit than that. Okay, in that case, well, you have a leading digit is non-zero. So you have at least 1 copy of q to the rth power. So n is bigger than or equal to q to the r. Okay, so that's fine. Let's on the other hand, n could also be written with all the coefficients up to power s. Okay, so this is the summation we have. Remember that bj is coefficient anywhere between 0 to q minus 1. So the largest it could be is q minus 1. So if I replace bj's with all q minus 1, I would get a bigger number, or at least as big number as I had before. And I'm going to use the homework 3.35 again. So if I factor q minus 1 out, then I could write this as this divided by q minus 1, which cancels out. So I'm doing this for the 3rd time, so I skipped a step. But this could be written as this using the homework we had before. And remember, R is bigger than SS, so R is at least S plus 1. So if I replace S plus 1 by R, I'll get something that's equal or bigger. But see what we have now is n is greater than or equal to q to the r, and also less than or equal to q to the r minus 1, which is, you can't be bigger and smaller at the same time. So that is that is impossible. Okay. So let's look at the case where we have the same number of digits. So R is equal to S. We know that the leading digit, A sub R and B sub R, are both non-zero. So if it's non-zero, we could subtract 1 from each of them and get a smaller number that has 2 different representations for, namely, n minus q to the r. But that's impossible because n was supposed to be the smallest number, which q-ary expansion was not unique. So that's a contradiction there. So there have to be one way to write any number n. Okay. I know that was a lot to take in, but that's the end of the proof. Okay. So that was a involved proof. You might be thinking, like, why are we going through these complicated constructions? Like, we already know that numbers work. We've used it ever since you learned about it in elementary school, or maybe even earlier. We're going over this because first we want to make sure that number systems really does work. We want a logical proof. But this is the type of construction that's actually used frequently in mathematics. To name a few, you might be surprised that, okay, we have existence and uniqueness of decimal expansion. That we kind of knew already. But you might have not realized that if you're talking about not natural numbers, but maybe real numbers, we could do something similar with like a decimal expansion and put a decimal point and more digits to represent any type of real numbers. So you could have a decimal expansion for any real number. In that setting, every number does have decimal expansion, but it's actually not unique. So you might ask yourself, in fact, I encourage you to go through the proof again, maybe running the video again, and work out exactly at which spot the uniqueness proof fails. Okay. Other places where you might use mathematics like this is that adding up different powers. These are similar to what we call like polynomials. And polynomials are used in lots of different things. So in abstract algebra course, you might use this construction called rings, and that's a popular place where you might use something like this. I worked with computer science students' capstone project, where we had this type of encryption method called learning with errors encryption algorithm, and you use exactly this type of construction there as well. So it's used for encryption. It is also used in what's called generating functions in combinatorics or even probability theory. So this is a type of this like coefficient multiplied by different powers of something. This is a construction that's used over and over, so it's very important. Okay, let's kind of go back to the notes. This was what's called existence and uniqueness type of a theorem. And I just kind of want to take a moment to say how important these type of questions are. So like as we learn more about mathematics, it's important to know what kind of questions mathematicians ask and answer. And anytime you have a new construction or new type of problem, the two questions you should first answer is, are there any solutions, or is there only one solution? Is there more? So if you've taken course on differential equations or matrix algebra, you might be familiar with like those type of questions that gets asked in those settings. So follow-up question to something like that could be, okay, if the solution exists, how do we find the solution? So in the proof of existence, maybe you have to construct a solution, find a solution to say that it exists, but sometimes you could prove something exists with a contradiction or something. So you might actually not have a way to systematically find a solution. So that could be a question that could be asked. This is more going on the computer science side, but once you have a problem that has a solution, you might ask, what's the quickest way to get to the solution, or how efficiently can you solve the problem? And that could be an important question as well. For example, the way encryption methods work is that, there's only finitely many combinations of ones and zeros. So you could eventually break any kind of encryption. But if there isn't an efficient way to solve that, then it's effectively impossible to solve it within the lifetime of the universe or something. Because there's no efficient way to solve it, but there's efficient way to encrypt it, if you have the encryption or decryption code, then it's a useful encryption system. And we might hit on something that kind of splits the type of question that some mathematicians are interested or not interested in. There are types of mathematicians who are okay with knowing that something exists and moving on. Okay, solution exists, so let F be the solution, and then move on with the problem. Or some might not be satisfied with the problem until you have a systematic way to get to the solution or approximation of the solution. So sometimes people are not satisfied if it's not a constructive proof, like where you construct the proposed solution before you call the problem solved. So that's something to think about as well. Would you feel comfortable moving on just knowing the solution, not how to get to the solution? Or do you have to construct the solution before you believe it? I don't know. That's something to think about. This is where we're going to end the video here. See you.